Hi, this is Kelly Thomas, and I'll be speaking today on the use of bent poles as a detonation indicator. As an outline of what I'll be talking about, I'll give you some background on why we care about this issue, our overall approach to the analysis, then move on to how we calculated the drag and blast loads, how we performed the structural analysis, and then the results of those analyses. Then I'll wrap up with conclusions and future work and acknowledgments of the folks that supported this work. So as background, the HSE, Graham Atkinson's team, identified the use of slender columnar objects such as lamp posts, scaffolding tubes, fence posts, things like that, as a detonation indicator, specifically the deformation of such objects in a vapor cloud explosion being an indicator of whether a deflagration or detonation had occurred. And what they observed based on some test results and some analyses was that if a tube or post exhibited continuous curvature rather than a hinge, then that continuous curvature was indicative of a detonation. And we'll look at a photo on the next slide. This illustrates, it's a page from their report about what continuous curvature would look like. So this pole has this continuous curvature shape that they had concluded was indicative of a detonation. This is part of a vapor cloud explosion test rig where detonations had occurred. Now, of course, there's some elements here that don't necessarily show that same shape, but this one certainly does. So our overall approach was to try to develop an independent assessment on whether cylinder columnar objects could serve as an indicator of deflagration versus detonation in a vapor cloud explosion. The way we went about that was perform CFD calculations using our in-house beauty code, a blast wave target interaction code, looking at disk-shaped clouds since they're particularly relevant in some recent vapor cloud explosions that are suspected of being detonations. We use that to generate blast, pressure, and drag histories. Drag histories, density and velocity histories. And we looked at that from flame speeds of Mach 0.7 up to Mach 5.2. So a relatively fast deflagration all the way up to a detonation. And we looked at cloud diameter to height ratios of 50, 100, and 200. 200 would be fairly representative of what was present at the Buncefield and Caribbean Petroleum accidental vapor cloud explosions. And based on those blast pressure and drag load, density and velocity histories, we did finite element analysis using the LS-DYNA code to look at the response of poles to both the blast pressure and drag history combined. We picked a representative pole geometry and we looked at selected locations both inside and outside of the cloud. And again, our goal here was to determine is continuous curvature indicative of a detonation or not. For the drag and blast load, just so we're speaking the same language, drag load 1/2 rho v squared times drag coefficient times the area of the object. If we look at then peak drag pressure, the term in brackets 1/2 rho v squared. We looked at that dimensionless in a dimensionless form by dividing by atmospheric pressure, and then also dimensionless drag impulse, which is just the integration of the drag load with time. The first thing we did was look at both the scaled drag load and scaled impulse, which were defined on the previous slide, versus scaled standoff distance. So this is just the normal classical representation of blast curves, but this time we're looking at drag. In this case, these are spherical clouds. This is work we did earlier, but it kind of served as a template for the way we went about this. Now again, we're not actually using these curves to perform the analysis. We're using the actual drag history, that is density and velocity, but this is a way to represent those loads. As animation of the blast pressure histories that we got, this is for a cloud diameter to height ratio of 100, so this is the intermediate case, and looking at it both with flame speeds of Mach 1 here on top and Mach 5.2 here on bottom. So we can look first at the Mach 1, and we can see the flame front burning through the cloud, and the blast is centered around where the flame front cloud interaction is, and then we get out to the end of the cloud. And in the case of Mach 5.2, on the same axis, up to 10 psig, same thing. Obviously, the flame front's moving factor of 5 faster. But that's just to give you an indication of the blast pressure histories. In terms of the drag history, first we'll look at the peak drag pressure in Pascal, so not in dimensionless terms, and the next slide would be dimensionless terms, as a function first of cloud position divided by cloud radius, so not in dimensional terms. We'll look at that again on the next slide. So in the green, we have the Mach 5.2. Then the black is Mach 1, red is Mach 0.7. The curve grouping out here is our spherical clouds, and again being plotted from the edge of the cloud. And then with the disk-shaped cloud, the drag loads drop off quite a bit faster. And the solid lines here are our cloud radii of 50, then cloud diameter height ratio of 50, then diameter height ratio of 100, and then 200. Now, if we look at this in dimensional terms, again, R-bar scaled standoff distance for scaled drag. The curves begin to collapse a little tighter. Again, Mach 0.7 in red, Mach 1 in black, and Mach 5.2 in green. And the curve dropping off faster here is our spherical drag load, but we start to get a coalescence of these loads when we plot them in dimensional space out a bit past R-bar of 1. Now again, in the FEA analysis, we're using the actual drag and blast pressure history and not these non-dimensional curves. This is more a way just to represent the results of the CFD analysis. So in terms of the finite element analysis, again, we used LS-DYNA. We picked a pole height of 30 inches, which is a little above the cloud with the diameter to height ratio of 50. We picked a half-inch outer diameter and fixed it at the base so it's cantilevered, and used kind of a standard steel. We varied the thickness of the pole, so the thickness to radius ratio, to achieve deformation. That is, if we had a pole that wasn't undergoing any deformation, then we would make the thickness a little bit less so it would deform under the prescribed loading. Conversely, if we had a pole that was slamming into the ground, well, we'd make it a little thicker. What we wanted to see was pole deformation, and whether that pole deformation was exhibiting continuous curvature or not. As I think I mentioned earlier, we looked at locations both inside and outside the cloud, and we considered both the blast and drag loading. The structural analysis tries to account for most of the major effects here. We account for the reflection of the blast load off the face of the pole, although that is of fairly short duration. For pole locations inside the cloud, we limited the reflection factor to 2.5, since based on our experience, that's a reasonable value for a reflection factor inside a detonating cloud. We looked at and we included deformation of the pole, that is, as the pole begins to deform and bend over while you're changing the nature of the drag loading relative to the gas flow. We also included the velocity at which the pole was going over, since that changes the relative velocity of the gas rushing by it. And we varied the drag coefficient. We varied it as a function of blast pressure using a high explosive relationship, which is admittedly approximate but captures the effect. In terms of results, the following plots, I'm going to go through a whole sequence of them, and then at the end we'll show all plots on one slide, which will be a little bit easier to understand. But just so you have a guide of what we're going to walk through, first the kind of squattest cloud, diameter height ratio of 50 at all 3 flame speeds, then going all the way to the diameter height ratio of 200, all at the 3 flame speeds. For each cloud geometry flame speed pair, what we're looking at is the response of the pole, and we'll look at it graphically, at selected locations both inside and outside the cloud, and I'll have a line that shows where the edge of the cloud is as a reference point. For several locations, we looked at alternative pole thicknesses in order to either decrease or increase the amount of deformation. Where we see things that we think or we believe clearly illustrate continuous curvature, that is, the the indicator of a detonation that we're exploring, we've highlighted those in red. Where it might be, but it's not really clear, we've highlighted it in yellow, and everything that's not highlighted is clearly not continuous curvature. Okay, with those provisos, look first, diameter height ratio of 50 and a flame speed of Mach 0.7. So we can see that inside the cloud, we've got a few that look like they might be continuous curvature and bending back towards the center of the cloud, and one at the edge of the cloud that might be, and just past the outside of the cloud. If we change the thickness, we can push these two yellows that are kind of maybe continuous curvature to more certainly continuous curvature. And then we have a number well outside the cloud that are not continuous curvature. And again, this is Mach 0.7, so clearly not a detonation. If we go to Mach 1, we see kind of the same thing. We've got a few that could be continuous curvature. If we change the thickness to a radii ratio, then we can get it to continuous curvature. In this case, we've got them pointed away from the center of the cloud. And if we go all the way up to Mach 5.2, again, we have a few that might be continuous curvature. If we vary the thickness to radius ratio, we can convince ourselves that we can get to continuous curvature. And again, these are away from the cloud, away from the point of ignition. If we increase the cloud diameter height ratio now to 100, again, there's a few that might be continuous curvature. We vary the thickness, we might pick up another, but again, this is at Mach 0.7, or clearly a deflagration. We go to Mach 1, again, we've got a few that could be, and again, they're pointing away from the center of the cloud. And if we go all the way up to Mach 5.2, so now we're in a detonation, we only get one that we think might be continuous curvature. Now, if we extend out to the diameter height ratio of 200, again, that would be kind of representative of, in the right ballpark for Bunce Field or Caribbean Petroleum, a flame speed of Mach 0.7, so a deflagration. We get one nominally that might be continuous curvature outside the cloud and pointing away from the center of the cloud. If we change the thickness to radius ratio, we can pick up a few more, and these are pointing back in towards the center of the cloud. These are all deflagration. Mach 1, again, we get a few that could be continuous curvature, one pointing in, one pointing out. And if we go all the way up to Mach 5.2, nominally we didn't find any under the detonation case, but if we make the pole a bit thinner, we get one that, well, perhaps there's some continuous curvature, but this is kind of hinge-like as well, so not clear. Now, if we put all of them on one plot, and I realize, of course, you can't read the numbers here, but they're the same ones that we just looked at. So the top row is Mach 0.7, the middle row is Mach 1, the bottom row is Mach 5.2. The first column, that on the left, is the diameter height ratio of 50 cloud, and the one on the right is diameter height ratio of 200. In the middle, of course, we have 100. And again, where we are fairly convinced what we're seeing could be classified as continuous curvature, we've made that in red. Where it's maybe, we've highlighted it in yellow. Again, the green dotted line represents the edge of the cloud. And where there are two rows of data, for instance, here in the upper left, why the bottom one is where we made the pole a little bit thinner in order to get more deformation. But you can kind of clearly see here that the continuous curvature isn't limited to just the detonation case. It shows up at lower flame speeds. And furthermore, for any of the flame speeds, the response depends a bit on what the diameter height ratio is, as well as where the object being deformed is. So what are our conclusions from this? Well, as you could see on the last slide, at least in our analysis, continuous curvature is not a definitive indication of detonation. This deformation of this type, that is of continuous curvature, or things that could be classified as continuous curvature, can be produced at multiple flame speeds, and it depends on the cloud geometry, the object characteristic, and the object location, whether it's inside the cloud or outside the cloud, and for either of those, how close or far away to the center of the cloud it is. Now, this is hardly a definitive work. We've taken a given pole geometry, a given set of parameters, and examined them. However, it could certainly be extended and refined. There's a lot more that could be done here. We could consider other object parameters, such as the height of the pole or columnar object, its shape, its whether it's round or square, its support conditions. We considered just a cantilever, but clearly in the photo that I showed you from the HSC's work at the very beginning, that was a pole that was fixed on both ends, or supported on both ends. We could look at a greater range of flame speeds, although we did cover from a fast deflagration to a detonation. We could look at alternative cloud geometries. Certainly we could go back and look at intermediate disk to height ratios, or look at spherical clouds, or what have you. Lastly, although this would be a big challenge, and in our work we did the CFD analysis, and then we used that as an input to the structural analysis. Obviously a couple analysis could refine the results a bit. Lastly, I'd like to make some acknowledgments. First, the Explosion Research Cooperative. This is the organization that funded this work. The Explosion Research Cooperative, or ERC, is made up of currently 21 companies, mostly, but not exclusively, within the petroleum and chemical processing industries. And the ERC has been engaged in trying to push forward and refine blast load and structural response predictions and testing analysis since 1993. So it's been around a good long while and is going strong. I would also most definitely like to acknowledge my co-authors. Will Lowry actually did all the CFD analysis, and Barry Bingham actually did all the FEA analysis. And then they graciously allowed me to give the presentation. Thank you very much.